on it eventually.
Let's start. So, welcome to this week's Colloquium. It's my great pleasure to welcome Alex Bronstein. Well, not on campus, because he's on campus anyway at the moment, but through the lecture hall. So, a little bit of background. Alex studied electrical engineering and computer science at the Technion, where he's also now a professor currently, and chair of the Intelligence Systems, what's it called? Center of Intelligence Systems. So Alex's main research interests are along theoretical and computational processing of geometrical data, but he's actually very broad in his interest, as you will see today as well. He has won numerous awards for his research and grants, including no less than 4 ERC grants so far. Apart from his academic career, he's also a successful investor and entrepreneur in the tech direction. And if you visit his homepage, you'll see he's interested in a lot of other things as well, including poetry, music, and maybe he'll play a little piece for us.
No chance.
No, worth a try. Alex is actually spending a year on campus here as a sabbatical visit, and he's interested in new collaborations and intellectual stimulation, mainly from the direction of physics or life sciences or anything related to his geometric interests. So if you're interested in that direction, just join us for lunch afterwards, or come to the Arrow Bar for the coffee session at 1:30, I think it starts. And with that, let's welcome Alex. We're looking forward to your talk on learning to see in the data age.
Thank you, Christoph, and thanks for the thank you. Well, I still need to merit that one. Thank you for hosting me today and in general for this sabbatical year. So I wanted to modify the title a little bit because I wanted to say a few words about acoustic imaging as well, so it's also learning to hear, not only to see. So I wanted to describe, to share with you some adventures that I have been having in this domain that can be broadly described as computational imaging in the past few years. And just to start with one picture that is worth, I don't know how many bits, but basically we, of course, humans and many other animals, we perceive the world through pictures, right? This is a schematic depiction of the visual cortex in our brain that does all the processing. It's a pretty big by volume and by area, big piece of processing hardware. And of course, since the dawn of our civilization, we tried to communicate in images as well, right? So this is one of the earliest cave paintings that is about 40,000 years old. Of course, this is a very laborious process, trying to capture the visual world. So humans always tried to streamline, to automate this process. And of course, you certainly know this device. This is a camera obscura. It became widespread in Europe probably about 300 years ago, but it was probably like most things were invented by the Chinese about 2,000 years ago. And it was one of the first imaging devices, of course. A pinhole camera that allowed to project light from the world onto a screen, and then artists, and I think bad tongues say this about Vermeer, they use these devices to paint his photorealistic paintings. But of course, you still needed a painter to capture the image, and what made a true revolution was the invention, probably an accidental invention of the photographic process that made the image persistent. And this is one of the first photographs with an exposure time of about 6 hours. I think we made quite a progress since then, right? Or at least apparently. We have more cameras, more image sensors in this audience than the number of people, maybe by a factor of 3, I would say maybe by a factor of 5, right? If you just count all the cameras that we have in our smartphones. So of course, these are marvels of engineering and science and technology, what we have in our pockets, right? They completely change the way we communicate, the way we interact with people. But if you think in principle, the design of these cameras is no different from the camera obscura that was used 300 years ago to entertain the noble. Basically, what we have is some piece of optics. Instead of a hole in the curtain, we now have slightly more sophisticated objective lenses, but the idea is the same. The objective lens collects light from the scene, focuses it on a plane. It was just a paper screen in the camera obscura. Now we have digital sensors that are sensitive to light. They convert photons to electrical signals. And then we send it to an observer to look at the image, right? This is how our digital cameras work. But of course, in the digital era, we have some amount of processing that we can put between the sensor and the beholder that does some nice manipulations of the image. And of course, in our phone, we never see the raw data. There is a lot of processing going on without us even noticing that. But still, in principle, what you see on the sensors is more or less what you get, up to some processing. But now we have much stronger processing abilities on the digital side. So we can play this game. We can put more processing power and then go crazy with what we do in the optics and in the sensor electronics and in all that analog part of the camera. So the image won't necessarily be intelligible to the human beholder, but after we do some processing, we can actually recover a nice-looking image. So this is the idea behind computational imaging in general, and I think this is a very interesting photo. This is a table prototype of a CT machine from the early 70s, for which Hounsfeld and Cormack got their Nobel Prize. This is the first reconstruction that took about 5 hours on computers back then. And what is interesting, if you see what the detectors collected, the X-ray tubes collected, the X-ray detector collected, there is no image of this brain phantom whatsoever visible in the raw signal. You actually need to apply a computational procedure to recover it. So what I would like, however, to address is a more novel, more emergent situation, is when the image is not intended for our human eyes, but it is actually it is consumed by some machine intelligence system. For example, in autonomous driving, actually having a human in the loop would not be productive, probably even harmful. So you now look at this system that has a camera that was designed to produce a nice image for the human being, but its product is consumed by a machine vision algorithm that might have completely different needs. So I would like to ask you this maybe a little bit provocative question, but do we need an image at all? If we want, for example, to detect pedestrians in a vehicle perception system, why do we care about seeing a nice image? Maybe we want to see something else that is indicative for the success of our end task. And then we can, of course, in the era of learning, we can try to learn all this perception pipeline. Of course, it is very easy to apply learning to the digital part, right? We do it all the time in computer vision nowadays. But I would also like to apply learning to the analog, to the hardware part, to designing the system for some optimality of the end task at hand. Okay? And I believe my personal wild speculation is that nature did it for ourselves and other animals for tens of millions of years. And the more we trust that guy on the right, the less we care about seeing a nicely intelligible image in the process. Okay, so and basically what I will show you next will be some of my group's exploration in different modalities, different domains of imaging. Of course, the most obvious one is optical imaging with regular sensors, but then I will show you some ideas around acoustic imaging, MRI, and other medical imaging modalities. I promised radar and LiDAR in the abstract, but I would like actually to show you more acoustics, so I will drop these ones. And then I would like also to show you very similar ideas can be applied to engineer other things, and I was particularly involved in an interesting project of designing quantum light sources, basically designing entangled photon pairs with specific properties in a way that it was very similar to what we did with imaging systems. So I think that can be useful. Okay, so let's start with this unsung hero, or actually very well-sung hero. If you pick this device from your pocket, you see basically this piece here is the thickest part of the phone, and arguably this is what sells it. This is what forces you to buy the new phone, except that also the battery that expires after 18 months approximately. But basically, what really drives it is you want to push more pixels into it, right? You want to make it thinner, you want to make it smaller, and at some point you hit a limit of physics, right? You still need to count photons to get a signal, and especially when you want to take an image, let's say a selfie of yourself in the nightclub, you don't have enough light for that, right? And it's incredible that this multi-billion market is driven by these very mundane needs. But basically, what you could do in theory is, okay, let's just drill a bigger hole in that camera, right, and let more light in. If you do this, well, of course you have some focusing mechanism in your lens that will focus the lens on an object, but then if the object moves closer, the image will focus behind the sensor, or if you move it farther away, it will focus before the sensor, right? So basically there will be some range of depths that photographers call depth of field, where the image stays in focus, and you will suffer from myopia or hyperopia beyond that region. And by the way, our eye does the same. If you drill a big hole, that depth of field will be very narrow. That's the price you have to pay. On the other hand, you will have more light coming into your camera. So what we wanted to do, okay, let's try to build a camera that has a big aperture, but has the depth of field of a narrow aperture camera. So what we did, we placed an optical element, a diffractive optical element, a phase mask that manipulates the incoming wave front in a way, roughly, that different colors focus at different depths. Okay. So then what you see on your sensor is this kind of weirdly blurred image, and photographers will call this chromatic aberration. You intentionally introduce chromatic aberrations that optical engineers worked so hard on removing completely from your objective lens. But what you get in exchange is that one of the chromatic channels stays in focus for a very wide range of depths. Okay, so you have sharp information, you have high frequency information in the image, and you need a computational process to recover it. So basically what we did next is we learned, of course, a neural network to reconstruct the image from these blurred chromatic channels, but we also simultaneously designed the mask. Of course, you need a differentiable forward model for this, but fortunately these kind of things are easy to simulate. Train this on simulation, and we got, this is an actual optical prototype with a clear aperture, I think, now I don't remember the F number, about 2.8, I think, with a pretty standard mount lens. And what you see on the right is the process of reconstruction with a phase mask, about 2 times improved MTF, modulation transfer function. Okay, and this is how the phase mask looks like. Of course, the Z dimension is greatly exaggerated by about 2 orders of magnitude. These kind of carvings, we etched them on glass, about 2 micron high. And this is just this phase plate mounted into a regular consumer lens. Okay, but then what we noticed is that this kind of weird blur that we get actually carries with it depth information, because the amount of blur that we have for different colors changes with depth. So if we analyze how pixels blur in different chromatic channels, we can actually infer depth. So what we did next, we created a depth camera. So again, another neural network that recovers depth from this defocus, and a completely different set of phase masks designed specifically for that. And with that, we get a single aperture, single exposure, completely passive depth camera. It, of course, cannot compete with active range sensors, but it competes very nicely with, for example, with light field sensors that have huge apertures and are probably orders of magnitude more expensive to manufacture. And actually, if you want to manufacture this thing, you don't need to manufacture a separate phase mask. It can be made part of one of the optical surfaces of the objective lens. By the way, I forgot to tell you, let's make a colloquium really colloquial. If you have any comments or questions, please feel free to interrupt me, okay? Okay, so I would like to show you another idea around designing optical imaging systems. I'm sure that you've seen this BBC series, Planet Earth. I think it was filmed in the 2006. Yes, please.
Since you want questions, so
yes.
why doesn't my phone have that?
Well, so we actually, okay, it's a great question. Why don't we see these things in regular phones? So we tried actually to make something commercial out of it specifically for the cell phone market. There are very, let's say, untechnological and unscientific reasons why this doesn't make sense. First of all, they are extremely dependent on existing supply chains. They won't buy components from a startup company. And also they have negative margins on the camera. So adding anything else. So we tried to convince them that you can actually simplify the autofocusing mechanism, but it is pretty harsh to get to this market. We didn't insist too much, but I guess this could be an interesting addition to the smartphones. I'm actually more interested in trying to do something maybe in microscopic imaging. I think it's more interesting. There you don't have so harsh limitations. Yes.
Isn't it depend also on having all these three wavelengths present within your observing? Like if the image is very monochromatic, if you're imaging a full room, won't you be able to not get?
Yeah, of course. So of course, the ability, so your ability to recover, let's say, depending on your application, let's say for the extended depth of field imaging, your ability to recover basically unblurred images depends on how much information you have in the chromatic channels, right? But if you have very uninteresting, very let's say, very white image without any features, probably you don't care about blur because the blur won't affect any high-frequency information anyway. So you want high-frequency information. You typically get plenty of that in, let's say, a 40-megapixel camera, right? But if you have completely unchromatic image, that would be a problem. For the depth recovery, it is more a problem. If you have a very dull, very smooth part of the image, your depth estimation accuracy there would be poor. But again, with a very high resolution camera, typically even a very smoothly looking material exposes some non-trivial features that you can estimate blur from. Okay. So going back to Planet Earth, that was probably the highest budget documentary series back then. $25 million or pound sterling, I don't remember exactly, but very, very high budget. And they used this kind of military-grade equipment. They mounted gimbaled cameras on helicopters to do these amazing shots of lions in the savannah. And nowadays, well, guess what? You can probably do it with this $1,000 device that fits into your hand. But basically, again, conceptually, the technology is the same. You have this mechanically stabilized camera. This is what is called a gimbal. It's a mechanical stabilization device. Of course, it gives really breathtakingly beautiful videos and very smooth photos, but it is a very costly device, not only in terms of the bill of materials, but also in terms of system cost. It takes weight and it takes power, right? You need to operate motors that stabilize the camera all the time. So what we tried to do is to create an airborne camera, a drone-mounted camera that has no mechanical gimbal. So we call it a digital gimbal. So for that, what we do, we use a fast frame rate, high frame rate camera, and don't think about anything crazy, just whatever you have in your phone is enough, a few hundred frames per second. Then we take a burst of frames. Of course, they suffer from two phenomena, right? If you expose a frame for a long time, you have motion blur. If you expose it for too short time, you have noise, right? Because you don't collect enough photons. So you take a burst. You need to align these images because there is some motion of the camera and motion of the scene. And then you would like to do denoising and deblurring simultaneously, right? And of course, this is done by learning algorithms. This is a pretty complicated task. We didn't invent too many things here. Basically, there are some already existing works. But basically what we tried to do, and it works pretty well if you engineer it correctly. This is just a resolution target. You get, here the camera was just put on a vibrating platform. It gets a lot of blur. If you do this processing, you get quite nice resolution. But basically what we try to do next is to try to control, to learn exposure times for the burst. So basically you can expose a sequence of frames to different exposure times. And then things get more complicated because you need to align and denoise and deblur images that look very differently because of the different amount of blur, different amount of noise, but still this task is solvable. And basically, I would like to show you this trade-off. Oh, sorry. So of course, if you want to now to learn the exposure times, you need to model the entire sensor in a differentiable way. So what we have, basically what we built is a differentiable pipeline for the camera model that has optics, mechanics, and a sensor model. The tricky part is how you make all the stochastic part of the sensor. Basically, low light imaging is dominated by shot noise that has Poisson statistics. How you get that part as a deterministic neural network with trainable, maybe with some trainable parameters, and have the stochasticity as fixed inputs to the neural network. And this is done specifically in our case. We just generalized the regular gimbal, the regular gimbal softmax trick that is used for that purpose. So as the result, we can train the exposure times, and when you do that, you actually get much sharper images, much nicer resolution. And so this is the trade-off that you see. What is depicted here? So this is a burst of 3 frames. We use the central frame as the reference, and this is the distribution of the exposure times that we're giving to the different frames. Vertical axis is the average illumination in sensor photoelectrons per pixel, and this is the mean blur in pixels. Okay? So what you see is that when you are noise limited, you try to get highest exposure in the middle frame to get more photons, because blur is not an issue. When you are motion limited, then you would like to get the shortest exposure for the middle frame to get the sharpest possible image because you are not noise limited. And then you have basically all this kind of, I would say, quite obviously right selection allocation of the times for all the cases. And another interesting thing is that when you learn this kind of exposure, what this image shows is the amount of the influence of each pixel from each of these frames in each of the output pixels. So you see in most places, you use them all. So that's why you see white. You use the leftmost frame, or the previous frame, the current frame, and the following frame. And only in places where you have very sharp edges, you take that from the middle, which has the sharpest information. It has the smallest exposure. And this is just an example of a real camera. We didn't fly it because it was too heavy in our prototype, but we put it on a vibrating platform that had approximately the same vibration modes as a real drone that we recorded, and it produces quite nicely looking sharp images. We tried to extend it to videos as well. A question, please?
Because you make a comparison with respect to the digital gimbal. Like, if you compare to the mechanical one, because they're not perfect anyway, like, are you better, or are you like, imagine that it's cheaper and more practical, and how do you range?
Yeah, I think so. I wouldn't lie. If you, of course, compare to a mechanical gimbal, that would be rock steady and perfectly looking. I think we still get very good performance, especially if the vibrations are similar to what you trained on. Basically, in terms of frequencies, in terms of the extent of blur that you see in the images, I think we get pretty good images as well. So we didn't actually do any comparison with a real mechanical gimbal. Okay, so of course, what is interesting to do here is to make it adaptive to basically to adapt the exposure times to the content of the frame, to the amount of blur. We played with it not very successfully, but then basically we moved to different topics. So, but it would be, of course, interesting to continue in this direction. But speaking about drones, I would like to show you some other projects. Yes, please.
Did you record the actual vibrations for this setup?
Yes, we recorded an actual, so it's not, we didn't record, our industrial partner that was actually building the flying platforms, they recorded using very precise IMUs and some laser sensors, they recorded the actual vibrations.
And did the system take the vibration?
More or less, we tried to match the power spectrum. We tried to match the power spectrum.
Yeah, but do you have something like an accelerometer? Or
Yes. Yeah. Well, so not an accelerometer, we tried to estimate from the camera basically the motion, and we looked at the distribution of the vibrations in frequency, trying to match that power spectrum. So it was a rough match, not an ideal match. Just to emulate.
when the system is operating, does it give information on the acceleration itself?
No, okay. Yeah. No, so we didn't use any IMU information for the reconstruction of the image. Of course, that would help. The problem is that you cannot put the IMU on the sensor itself. Putting it on the drone is a little bit difficult then to infer the dynamics of the sensor itself. Okay, so staying with the drones, I would like to show you some different modalities, just for the sake of change. So today you can use drones to take the drone-y kind of selfie images, right? But one data channel is glaringly missing in the drone, right? You don't have sound, right? And this is, of course, because if you tried flying a drone, it makes a lot of noise, right? And that noise, if you put, let's say, an array of microphones, that you will just hear that, the self noise that the propulsion system creates, so no sound. But basically, what happens, an interesting thing, if you place it in an environment, then you will hear, of course, the direct path of your noise that your rotors create, but you will also hear the reflected sound from the acoustic environment, right? Like in this room, we have plenty of echo and reverberation from the walls. And basically, now the game you can play, let's try to actively shape the propulsion noise in a way that you can localize and maybe map the environment by listening to that self-noise that interacts with the environment, right? So that's basically, it is a very strong source of noise. Clearly you can get some use of it. So this is what we try to do. Of course, the localization is done by learning. I will show you a few details again. And so far, we were successful in localizing in a known environment, or let's say roughly known environment. The next stage, of course, would be also to recover the geometry together with the localization, what is known as simultaneous localization and mapping, or SLAM. So typically, SLAM is done using visual channels, but acoustic SLAM is, of course, very appealing. Okay, so what you can see here, this is an acoustic simulation of the environment. This is actually an actual recording of a single rotor, and the same is just a geometric simulation of the environment. It's actually very interesting how you record these things. So you can see they create pretty non-trivial pressure fields. Of course, this is slowed down by about 100 times. And when you put it into a room, I don't know, maybe you don't see a dramatic change because the biggest signal that you see here is the direct path, but about, depending how close you are to the wall, about, let's say, from 2 dB to 8 dB below, you actually see the echoes, right? So that means that with even a very modestly wide A to D, you can get those features very, very easily to your system. And also, you can see that it responds to the location in the environment. Okay, so you see the signal is different because it interacts differently with the walls. Now we over-engineered it humongously, but what actually works very nicely is phase modulation of the rotors. So, phase modulation. So you see, when you change the relative location of the rotor blades, still spinning at the same frequency, and therefore creating the same amount of thrust, you see completely different acoustic fields, right? So basically, if you change the phases while you are, let's say, hovering in a place, you measure different things, right? You measure the response of the environment to different excitations by this acoustic field. So you have more equations for the forward model just to put it in simple words, right? So basically, you can actually get very, very accurate localization from these, like, I don't know, to about 2% of the room dimensions. And it is pretty robust to modeling errors. What is hard, however, is to put this into a control system, because if you want to change the phase, the derivative of your phase change will affect the angular velocity of the rotor. That will create thrust, right? You create more thrust, you will topple. So basically, we built this control system. It can actually fly and record sound. So we built everything here custom, including the analog circuits. But basically, it's a complicated control problem, actually somehow not really addressed in the literature for some surprising reason. So we have two types of degrees of freedom that we would like to control. We have the location, basically the linear dynamics. We have the angular dynamics, and particularly important for stability are the roll and the pitch, right? So we want to control them fast. Linear dynamics are probably not as important. If you get to that point in more time, nothing bad will probably happen. So we have a slow and pretty trivial PID controller for the location. We have a much faster and a very non-linear controller for the orientation. So we use reinforcement learning to actually learn this controller. And basically, these two go into an inverse torque dynamics model. So basically, if I give you torques, I can model pretty straightforwardly. It's a non-linear dynamical system, but I can model you basically how this will affect your linear and angular dynamics. And you want an inverse model of that, right? Because you want to drive it with your desired location and orientation and get the torques, okay? And the problem is, of course, how the heck do you get your phases, the rotor phases in? So the trivial idea that we tried, and it worked pretty well, is just to think of phases as a disturbance directly at the level of the torques. We have this phase controller. This is the fastest part of the system. It is a high pass. When you put it into this closed loop system, it just acts as a high frequency filter, a high pass filter. So basically, we design the target functions. We know the response of this controller. So we need to design the phase modulation in such a way that it doesn't contain too many low frequencies. So when you integrate it in enough time, you basically have no net thrust added to the system, right? And basically with that, we just use a regular electronic speed control for the motors to actually drive them with a voltage signal. So we already have flying prototype working with that, but yeah, what we would like to get to is, of course, doing mapping of the environment, not only localization. Okay? So speaking already of acoustic imaging, so it wasn't exactly imaging. We don't really get an image, but we solve a specific task, again, with the design of the analog and the digital part. Of course, we would like to go crazier. We have, actually, the system is hugely over-engineered. We can make the drone sing your favorite song. We never actually used this capability, but we also wanted to try designing the blade geometry to produce the most favorable sounds. Yes?
As you mentioned, say that you locate yourself in no room or
yes.
in slam, maybe just simpler obstacle detection so that it knows that it's close to a wall. Can this say easier done for unknown geometry?
So that is probably, so we thought a little bit in this direction. So you have some kind of a poor man's beamformer here. So you can have some directivity of the beam that you're projecting. So you can do this kind of directional sensing of very big obstacles probably without any problem, without assuming any model about your environment. So yes, a question? Yes, please.
I was just curious, would it help anything, for instance, like if you had an element
Well, so what we are trying to, what we did until now was entirely two-dimensional, but we have 3 degrees of freedom, right? Location and orientation. And actually, with the game you can play, you can actually rotate your drone or perform some path. For sufficiently short paths, the IMU measurements, the inertial measurements, would be enough to know how much you moved, right? And with that, create some kind of synthetic aperture, right? So you sense more equations in the forward model, right? So we haven't done that yet, but this is on the list of things that we would like to do. So with that, you can probably get, if you want to actually measure the environment, you can probably get much higher resolution than the wavelength working in the near field, right? So the wavelength for those frequencies, the fundamental frequency is about 50 hertz. It's about 6 meters in air. You can get much better than that. Okay. So going to ultrasound, I would like to show you a few more. How much time do we have until 12:30, right? Okay. So actual acoustic imaging. For that you typically need higher frequencies. So we looked into medical ultrasound. So in medical ultrasound, it is an active imaging system. So you transmit sonic energy into the body, and then you collect the reflected echoes to construct the image. So there are no moving parts in an ultrasound probe typically. It acts as a phased array. You have a line or maybe some convexly shaped collection of little transducers, crystals that vibrate at ultrasonic frequencies. And by delaying the phases to those transducers, you can focus the beam or you can create a wavefront of a desired shape. So this is called beamforming. You beamform on transmission, and then you beamform back on reception to form an image. Okay? So basically, typically when you do an ultrasound scan, and I'm sure that probably everyone here did an ultrasound scan, you see an image, and the way it is acquired is by focusing the beam and then steering it in space, typically just in one dimension, and the result you get an image. So this is very commonly accepted modality. The problem with it is that it is very slow, or it is unaffordably slow if you want to, for example, do cardiac imaging or to image something that is moving while you are scanning. So the typical answer to that in ultrasound machines, you can just turn it on with a click of a button. You can do either multi-line acquisition, so you spread your beam and move faster, or multi-line transmission. Don't ask me why they call these modalities in such weird names, but multi-line transmission means that you still have focused beams, but you scan with a comb rather than with a single beam, assuming that if the beams are spread far enough from each other, you don't have too many artifacts. But in practice, you do. So if you do multi-line acquisition with a spread beam, you lose resolution in this angular dimension. And if you do multi-line transmission, you have, first of all, you lose contrast. You can see here that the same feature here and here has much lower contrast with the multi-line transmission acquisition. And there are also some additional artifacts that might be created. So basically, the first thing that we try to do is to actually learn a reception beamformer to form a nicer looking image. And you can see this is the typical contrast loss that you have with a 6-time multi-line transmission, so multiple focused beams, 6 beams in a scan. And this is what you get with a learned beamformer, same speed, but basically image comparable to what you have with a slow single-line acquisition. What actually was much nicer to do is to learn the transmit beamformer as well. So if you learn the transmit beamformer, so the beam patterns that we learned actually didn't look like a focused beam at all. So it did look like a few beams, not necessarily focused. I don't have them for some reason in this slide. But then we get again, quantitatively comparable images with about 20 times faster scan when you tweak both the receive and the transmit. Okay? And again, with the drone acoustic imaging that I showed, we don't have a real beamformer, but we have a kind of a very poor beamformer, and then we can play with additional capabilities of beamforming, for example, trying to disguise your noise that you're making to the noise of some different aircraft or something like that. Okay, another medical imaging modality that I would like to show you is magnetic resonance imaging, right? And of course, I don't know, I will just briefly explain you the principle. It is based on what is called nuclear magnetic resonance, except that if you mention the word nuclear, you will probably decimate the number of patients that would like to use this machine. So that's why it is called MRI and not NMR in the clinical setting. But basically, the principle is very innocuous, actually. If you place atomic nuclei, or certain atomic nuclei, and in particular hydrogen nucleus, has spin, and it acts as a little magnet. So if you place it in strong magnetic field, they will all orient in the direction of the field. And the resonance phenomenon consists in, if you irradiate it with an RF pulse corresponding to the resonance frequency, they will emit that pulse back because of the resonance phenomenon. So basically, you need very strong magnetic fields to actually get signal. That's why this liquid helium-cooled superconducting magnet, this is what it is used to create these very strong, typically 3 to 7 Tesla fields, very uniform. But then the question, of course, how you get an image. So if you just get this kind of resonance frequency transmission from everything that is hydrogen-rich, like water and fat, you don't get an image. You get just little tone at one frequency. So basically, in order to get imaging, you can spatially vary the strength of the magnetic field. So the direction is still the same, but the field is slightly weaker here and slightly stronger here. And that gradient separates the emission frequencies, and the spatial coordinate now becomes the frequency coordinate. So you can acquire your image in the Fourier transform. So in the real MRI machine, of course, in addition to the big magnet, you have these, what is called gradient coils, superconducting magnets that change the strength of the field, and by manipulating them, you can orient the gradient direction in any direction you want. And basically, if you just keep that fixed, you can collect a slice in the Fourier domain, in the frequency domain. And what is done in practice, you change the gradients during the acquisition time, so you scan a trajectory in the frequency domain. Okay? And this is how the image is formed. So you program the trajectory, you get your signal, and you reconstruct an image. So people did image reconstruction with learnable algorithms. This community is very, very reluctant to accept machine learning solutions, but FDA is already approving machine learning specifically in imaging. So I think the barrier has been broken. But basically, what we try to do is to simultaneously learn the scan trajectory. So we learn the scan trajectory. That's the parameters of the hardware. And we simultaneously reconstruct the image together with that. Of course, like every physical system, this system also has inertia. So instead of mass, what plays the role of mass here is the magnetic inductance of the gradient coils. You cannot drive them with too sharp changes of the current. They would resist to such change of the current. And also, of course, there is a certain amount of current that you can drive before you quench the magnet. So you're limited in the acceleration and the velocity of the scan trajectory in the frequency domain. So subject to these constraints, we can learn the scan trajectories. So this is a typical 16-shot radial scan. You need these multiple shots actually because the signal decays, so you need to excite the matter and then read it out. And what you see here, these crazily looking trajectories, I assure you that they admit to the constraints of the machine. And what you reconstruct from them is both quantitatively and subjectively better with this scan. But then of course, you can also, a question? Yes, please.
Is it a real measurement or simulation?
So this is still emulation, I think quite realistic one. Now we have our new shining own MRI in the MRI center at the Technion, and fortunately, we have a timeshare of that instrument. So I have a student who is going to take it to the real machine. Of course, it won't work, because there are some additional things that need to be taken into account, like, for example, how you deal with inhomogeneities of the field. So you think that you are at that frequency, but in reality, you're not. These issues have been addressed pretty well in the literature, so we will need to adapt those techniques to our. Yes?
What do you use for ground truth to make sure that
Okay.
all of these values?
Okay, so these are static scans, very, very densely sampled, using Cartesian scans, so like hugely oversampled. There is Facebook released, I don't know how Facebook got to MRI, but basically Facebook released a very high quality collection of scans, from which basically also separate readouts of different coils that collect the data. So we used that. We were slaughtered for the emulation of this forward model several times in the real MR literature until we got it right. So yeah, I hope our emulation is correct. Yeah. Yes?
I have a technical question.
Sure.
Trajectories are longer than in the radial sampling.
So here, no, so they are not really longer. No. So it's the same amount.
The time of one scan the same in both cases?
Yes, one shot is exactly the same. Yes. So the number of points that you collect on the trajectory is practically unlimited. It's only limited by the sampling rate of your A to D. So that you can collect as many points as you want, but the duration, it matches the signal extinction approximately. So typically you have the strongest signal in the DC area. You design the pulse in such a way, but the amount of time you spend along this trajectory and this trajectory is exactly the same. Okay. Any other questions? Okay, so we tried, a question, please. Yes.
And the, say, MRI machine manufacturer, they give you such low-level access to the devices?
Under appropriate agreements, yes. So Philips, in our case, they gave us access. So this is a research machine. It's not a clinical device. It is approved for research, not for clinical use. So we can actually program our sequences. They have their own language that has a nice Pythonic interface that we can use. So we are only starting to step on this ground, but it will be exciting.
They have safeguards.
They have safeguards in terms of you cannot quench the magnets. That's sure. Yeah. So we also tried to learn scan trajectories for different tasks, like for example for segmentation or tissue recognition. So we consistently see better performance. And when you actually look at the trajectories, for example for segmentation, you see that for image reconstruction, you oversample. You have denser sampling of the DC area, of the low frequency area, where basically the approximate content of the images. And for segmentation, you actually sample more the higher frequencies because you want sharp edges. And it makes sense. Then we tried to extend it to, we have several works that I simply don't have time to publish. We did it for 3D, for volumetric scanning as well. That typically takes a long amount of time. Also then you can go either to dynamic scanning. So we have a work that does it for acquiring basically fast sequences of, let's say, of a beating heart or something that has dynamics in it. And also, there are interesting redundancies that you have in time, or acquiring more complicated properties like the diffusion tensor, for example, for diffusion tensor imaging. Those are very long scans, and there is a lot of redundancy in acquiring spatial properties and those diffusion tensor properties that require additional acquisition. So basically, we tried exploring these directions as well. And the last thing I promise, and then I will finish, I would like to show you kind of a reversed problem, if you will. So instead of imaging, I would like to create a light source that is, as far, again, I'm not an expert in this, but I know that specifically designing quantum light sources with entangled photons are used in quantum computing, quantum communication, specifically through the process of spontaneous parametric down conversion. So basically the process works as follows. It uses nonlinear optics. In our case, we have a crystal that has second order nonlinearity, so the susceptibility parameter the susceptibility tensor, the second order, basically part of the tensor, can change in space. We pump this crystal with, let's say, a green laser to omega frequency, and then it spontaneously decays into 2 entangled photons of half the frequency. There, of course, all the right physical properties need to be conserved, like momentum. So they come out as 2 polarized beams with opposite polarizations. You can put a polarized beam splitter, and you get what is called the signal and idler, 2 beams that exhibit some dependencies between them. Right? This is where entanglement comes to play. So you can actually measure the cross correlations between state of the signal, state of the idler, right? And for communication, you typically want to engineer this thing. You would like to create a light source that has properties in these correlation matrix. Okay? So basically what we can control is the crystal. We can actually build either 2-dimensional or 3-dimensional crystals. We can etch in them these nonlinearities of this susceptibility parameter. That is manufactured once. And then we can change the pump, the laser beam that goes into the crystal, and that can be modified with an SLM, with a spatial light modulator, practically in real time. So basically what we did, again, we created a differentiable forward model of this crystal, of this entire process. So we parameterize the pump, parameterize the crystal. We learn the parameters of the crystal and of the pump in order to get a desired pattern of photon correlations. So this is, for example, how these nonlinearity patterns, these are binary nonlinearity patterns, look in a crystal. The Z dimension is exaggerated. You have many more such repeating patterns, but basically this particular pattern and this particular pump with this intensity and this phase create, you wanted this kind of idealized 4 peaks. You get something that is slightly noisier but still high quality source. Then we have an experimental collaborator that currently confirmed basically the design outcome for 2-dimensional crystals quite accurately. There are interesting problems that arise in the practice. You would like, for example, to make this design process robust to manufacturing errors. So that is relatively easy. I think a more interesting question that we still don't know how to answer, you would like to design a single crystal such that by pumping it with different pumps will give you, for example, a variety of different outputs here. So you don't need to change that piece of hardware. You just modulate the pump in a different way. Okay, so again, I think that might be interesting. Again, the repeating motif here is that if you know how to build a differentiable forward model, then you can learn through it and design both the software and the hardware that's included. Okay, I would like to, of course, there are many people. This is a partial list of students and collaborators who worked on these adventures into the imaging world. Many of them already graduated, 2 will become professors soon. And of course, mentioned last, but those who pay the bill for this research, the funding agencies. And thank you very much. Thank you.
It's the first time that I host a talk where we have this beautiful cube to throw around. So is there any questions? And the rule is that the first question has to come from a student or postdoc. Otherwise we cannot leave ever. Any questions? Come on. Yes, thank you. Oh, this is so far away. No, don't shout. I want to throw.
It's soft.
Is this working? Okay. So given that SLAM works pretty well with vision, can you list some of the advantages why are we reinventing it with sound?
So why to use acoustic SLAM instead of visual SLAM?
Exactly.
Right? So multiple reasons. first of all, vision is much more expensive in terms of power and in terms of cost, right? So acoustic signals have a fraction of the bandwidth of an image. Typical, let's say, imaging system for visual SLAM would be in the range of probably several watts just for the cameras, and for the processing probably at least about the same order of magnitude. For acoustics, it would be a fraction, maybe 10 times.
The accuracy you said is in the order of meters.
Pardon?
The accuracy is in the order of meters, given the frequency of the sound.
Well, so in acoustic, so we get much higher accuracy. We get about, let's say, with our initial setup, we get about 5 to 10 centimeters accuracy in acoustic, so much lower than the wavelength, of course. Also, with those frequencies, you can see around the corners. You cannot do it with vision. You can also see in poorly illuminated environments or through some interacting medium like fog. So I'm not suggesting to use acoustics as the only modality, but it could be a good complementary modality. And basically, you have that noise already. It doesn't cost you a lot to exploit it for mapping and for localization.
I have a question about your K-space sampling, this MRI thing.
Mm-hmm.
So ultimately, you basically fill up K-space more than what you do in the radial sampling.
Yes, well, so you basically do this kind of
Right.
more wider excursions.
So what limits even further exploration? Is it the speed at which you can
Yes.
sweep the gradients?
The
or
dynamic
time
constraints.
clearances?
Yeah, exactly. Yeah, the dynamic constraints limit you from. So there are some works trying to basically to design typically random sampling with certain properties, like what people do in MRI with compressed sensing for probably 15 years, if not more, like works by Miki Lustig and others. But then you have these random samples. You need to connect them with the trajectory, right? So I think designing the trajectory in the first place is more useful, because then you can put all these kind of dynamic constraints during the design process.
Okay, so do you expect major hardware developments to make the sampling more efficient? Or because it's, if I understand correctly, now what limits you is the hardware, the gradient sweep, basically.
Yeah, but I think we are very far from actually reaching the hardware limitations of those coils. I think what really limits is the amount of noise that they produce. So for MRI users, you want to limit noise to, let's say, probably up to 90 dB, and that limits the amount of current that you can drive and the changes in current. So that is a much stricter limit than the physical limits of the coil.
Like this. Any final question? Oh.
Hi, Alex. Very nice talk.
Thank you.
I have a question. If you think about EEG data, is there any way you can apply your technologies to make that more specific to understand better where the signals come from, how they integrate?
Yeah, yes. With the EEG, I think we can do many things. So what we tried experimenting with the EEG. I didn't show it here. It's also an imaging system. So in EEG, at least when you sense through the skull, you have this discontinuity in conductance between the CSF and the skull bone, right? And it acts as a spatial low-pass filter. So you are unable to localize the sources, especially in the depth direction, right? But also in the angular direction. So what we tried to do with the EEG specifically. So we created some kind of a broken voltmeter, if you will. So we loaded an EEG cap with a network of electric impedances. We tried only ohmic impedances, but you can probably do it with capacitors as well. And then we modulated that network with frequencies much higher than the biological frequencies, so to about 20K, something like that. So what it gives you, it allows the current to flow between the electrodes. You essentially sense your sources through different forward models. So let's say you acquire 10 measurements with the sampling frequency of 2 kilohertz. That would, let's say, would be the limit of your physiological frequency. So you have 10 different measurements through 10 different forward models of the same source. And we showed both in simulation and we also actually built an electromagnetic phantom that you can localize much better, like an order of magnitude better when you do that. You have a much better determined forward model gain matrix that you can recover your sources from. In that particular case, we didn't know what to do with it exactly. So it was a good, nice exercise. We licensed it to a company that was doing some medical device, but I have no idea what they did with it. I think specifically for your applications, you have a much richer problem because you have a very dense electrode array, right? And then maybe you can design something crazier, like maybe some kind of compressed measurements as well.
Okay. Let's thank Alex again.
Thank you.
And then we can move all the remaining questions. Just come to the front. We go for lunch. And at 1:15 in the error bar.